हेलो स्टूडेंट्स, केमिकल बॉन्डिंग में हम मॉलिक्यूलर ऑर्बिटल थ्योरी का सेकंड पार्ट डिस्कस करते हैं। तो जैसे कि प्रीवियस लेक्चर में हमने मॉलिक्यूलर ऑर्बिटल थ्योरी के पोस्टुलेट्स डिस्कस किए थे और हमने कहा था कि एटॉमिक ऑर्बिटल्स दे आर इन एटम्स। एटॉमिक ऑर्बिटल्स are in atoms and molecular orbitals are in molecules. Molecular orbitals are in molecules. राइट तो जैसे कि हम एटॉमिक ऑर्बिटल्स को रिप्रेजेंट करते हैं जिस तरीके से 1s 2s 2p 3s, हम जो है एटॉमिक ऑर्बिटल्स को रिप्रेजेंट करते हैं 1s 2s, p के 3 ऑर्बिटल्स होते हैं 2px 2py and 2pz, right? And this is 3s orbital. But molecular orbitals are represented by sigma, pi, del, etc. Right? The molecular orbitals, they are represented by sigma, pi, del, etc. We will talk mostly about the sigma as well as pi. Right? So now we will talk about the electronic configuration, right, in case of molecular orbital theory. Electronic configuration. Electronic configuration, right? So how the electronic configuration is written here, we will follow the sequence sigma 1s, sigma star 1s, right, sigma 2s, sigma star 2s, or we can read sigma asterisk, right, sigma 1s, sigma asterisk 1s, sigma 2s, sigma asterisk 2s, right. Pi 2px equivalent to pi 2py, right. Sigma 2pz, right. After this, pi star 2px equivalent to pi star 2py and sigma star 2pz, right. Now how we will write the electronic configuration? First of all, as H2, there are total 2 electrons, right. Now how will the electronic configuration is written? In case of H2, total 2 electrons, we will write sigma 1s2, right. What about H2 plus? There is only one electron, we will write sigma 1s1, right? If we want to write the electronic configuration of Li2, right, lithium, and we know the atomic number of lithium is 3, right, and 2 lithium, it will contain total 6 electrons. Now how will we write these 6 electrons? Sigma 1s2, sigma asterisk 1s2, right? After that sigma 2s2, right? This is the electronic configuration of lithium, right? Now if we want to write the electronic configuration of nitrogen, how will we write? We will write it as, this is nitrogen, total electrons 14 electrons. Now we have to remember the order. We know nitrogen consists of atomic number 7 and 2 nitrogen will contains the 14 electrons. Now electronic configuration sigma 1s2, because we know SR will contain only 2 electrons, not more than 2. Sigma asterisk 1s2, right? Sigma 2s2, sigma asterisk 2s2, right? We have total 14 electrons, so up to here we have 8 electrons. Now pi 2px equivalent to pi 2py, right? We will put 2 electrons here and 2 electrons here. Now we have 2 electrons still pending, and sigma 2pz, right, and 2 electrons here. So this is the electronic configuration of nitrogen molecule, right? This is nitrogen molecule. So first of all we will talk about the bond order. Now what is bond order, right? So the bond order is half the difference between number of electrons, half the distance between number of electrons present in bonding as well as anti-bonding orbitals, right? Bond order is the half the distance between the electrons, between the number of electrons present in bonding as well as anti-bonding orbitals. Now simply we can write bond order equivalent to half, that is 1/2. difference between distance between the electrons present in bonding as well as anti-bonding. NB means number of electrons in bonding orbital minus number of electrons in anti-bonding orbitals. So this is the formula for calculating the bond order of a molecule, right? And molecule will be stable. Molecule will be stable molecule will be stable if number of bonding electrons are greater than number of anti-bonding electrons, right? That is, if bond order is positive, right? Now, how we can calculate the bond order, we will understand, but you have to remember one point here as golden rule, that bond order is directly proportional to stability. If bond order is more, stability is more, right? If bond order is less, stability is less. And next important thing you have to remember, that bond order is inversely proportional to bond length, right? This is also another golden rule you have to remember, right? And next important thing is the magnetic nature. Magnetic nature. Magnetic nature of the molecule can be of two types. One may be paramagnetic and other is diamagnetic, right? So paramagnetic nature will be when unpaired electrons are present in a molecule. Unpaired electrons are present, right? Suppose in the orbital we have unpaired electron, and that molecule, right, will gets attracted towards magnetic field, right? In case of diamagnetic, there are present paired electrons, right? Suppose in the orbital we have paired electrons, right? And in this case, repulsion towards magnetic field takes place. Magnetic field takes place, right? And I will provide the one shortcut here for competitive exam. If I will write here it as number of electrons equivalent to bond order, right? If we have 14 electrons in a molecule, the bond order will be 3, right? If we have 13 electrons, the bond order will be 2.5. You have to subtract 0.5 backward, right? If 12 electrons, bond order is 2. If 11 electrons, bond order is 1.5. If 10 electrons, right? If 10 electrons, bond order is 1, right? And if we have 15 electrons, bond order will be 2.5. If 16 electrons in a molecule, bond order 2. 17 electrons, bond order 1.5. If we have 18 electrons, the bond order is 1. You have to remember this, right? Now, after this, we will understand one very important thing, that in some cases when we draw the orbital energy level diagram or molecular orbital energy level diagram, the energy level diagram is different, right? Why it is so? I will write the question: why molecular orbital energy level diagram are different? Firstly, I will tell you the molecular orbital energy level diagram, right? The molecular orbital energy level diagram is drawn in this way. We have the atomic orbitals, and in center the molecular orbital will be formed. For example, we talk about the suppose we have a beryllium, right, Be2 molecule, and we know beryllium has electronic configuration 1s2 2s2, right? So there is 1s, there is 1s, right? Beryllium, there is also the beryllium, and here Be2 will be formed, right? Now, when two atomic orbitals combine, they will form two molecular orbitals, right? And these two molecular orbitals are in this way. This is also beryllium 1s2 1s2, and two molecular orbitals will be formed here, right? This is molecular orbital of Be2 molecule. Now we have two electrons here, 1s2 and 1s2 of another beryllium. we have total 4 electrons, 1 2 3 and 4, right? Now after 1s2 we have 2s2, right? I will write here 2s2, 2s2, right? And in the same way we have two type of molecular orbitals, right? This is 2s2, this is also another beryllium having 2s2. Now these type of molecular orbitals will be formed here because number of atomic orbitals combined will be equal to number of molecular orbitals formed, right? We have total 4 electrons, 2 here, 2 here. Now this is sigma 1s orbital, this is sigma star or sigma asterisk 1s, this is bonding and this is anti-bonding, right? Anti-bonding molecular orbital and this is bonding molecular orbital, right? Which has less energy. Bonding molecular orbital has less energy as compared to atomic orbital, right? And anti-bonding molecular orbital has higher energy as compared to atomic orbital, right? Same is the case here. Sigma 2s and this is sigma asterisk 2s, right? So in this way the orbital energy level diagram is drawn, right? We have to put in this way here energy, right? Or we can write energy, right? So upward energy is increasing. So if we talk about the N2 molecule, right? If we talk about the N2 molecule, so in which way the diagram is drawn?